Hello, everyone, and welcome to Working Group TAI meeting, the technical exchange meeting. And today's topic of our meeting is network time dissemination services. And we'll have 8 different presentations from National Metrology Institutes and the collaborators from around the world. I'm very excited to listen to very interesting presentations. We have very short time, that's why I'm rushing here a little bit. And every presenter has 15 minutes. So I request everyone to please respect your allotted time. This 15 minutes includes the time for questions. If your presentation runs too long, I'll try to keep you to the schedule. And if there is no time for questions, I invite everyone to questions on our forum and the website again at the end of the presentation. So without further ado, this is the list of the presenters. We start with Judah, then Adam, then Tatsuya, then Michael, then Nir, Albin, Claudia, and Andre. And I will be inviting you to start. So Judah, you are the first one. Welcome to the...
Okay, thank you. Let me see if I can share my screen. Let's see. Can everybody see my screen? Is that okay?
Yes.
Okay. Thank you. Let me go very quickly through the network time services that we run at NIST. We have 24 time servers at various locations, and we have 6 additional systems that provide technical support, monitoring, and accounting, and so on and so on. The servers are located at NIST in Gaithersburg, the headquarters of NIST, NIST in Boulder. We have some at the radio station WWV, and we have some servers in Jilla, which is where my office is. The Jilla system is really the master system in that it does most of the monitoring and control for the rest of the network, and that's done primarily because that's where my office is. We have cesium clocks at all the locations. They realize UTC NIST. They are monitored by GPS and Common View with respect to Boulder, but we don't use GPS for steering. The system is essentially independent of GPS, except in the very long term when we have to apply a steering correction to the remote cesium clocks because they tend to drift away from UTC NIST. The steering corrections are not very often, typically maybe every month. We have a 1 GB per second connection to the public network at every site, and that's the thing that supports the time service. As a round number, we are using about 30% more or less of the bandwidth that 1 GB. So we're using about 300 megabits per second at each one of the sites. We also have a private network, which is not visible to the public, and it's used for maintenance and upgrade and so on. Now, we have a number of different services. I'm going to provide initially just a summary of the services, and then I'll have some more detail about each one. We have standard NTP and SNTP. Those services are open access. We get about 1 million requests per second to all of the servers. About 95% of those requests come in IP version 4. About 5% come in IP version 6. The IP version 6 services were intended to grow. It was the vision of NIST that they would become more important, but that has not, in fact, that has not happened. The IP version 6 services have maintained a level of about a few percent since the system was initialized a few years ago. Now, we also have an authenticated NTP service, which is limited to registered users. It uses NTP messages with a digital signature, which I will describe a little bit more in another slide or two. We have 1,600 registered addresses at the moment, and that's growing slowly. The service provides, the service runs only on IPv version 4. There are some technical reasons for that, but the main point is that we have so few IPv6 users that it's hardly worth the trouble. We have many international users from pretty much everywhere. We do not have any users from Africa. We don't have any users in Antarctica, but we have users from pretty much everywhere else. We don't, there's no restriction on using the service. We provide services to international users if they ask for it. We also provide UT1 time service in NTP format that uses UTC NIST plus a correction for DUT1, which we receive from IERS Bulletin A. And again, the details are to follow. We currently have about 1,000 IP addresses. That is 1,000 systems that query that system. And again, it's IP version 4 only. The 1,000 IP addresses are probably not 1,000 distinct users. There are probably several systems at each site. We also have a number of services in other formats that I'm not going to talk about because this discussion is limited to NTP. Just for reference, we get about 26,000 requests per second in the time and requests for services in other than NTP formats. All the services are provided at no cost. So let me now go through a little bit more detail about each one of the services. The standard NTP supports NTP version 3, version 4, and IP version 4 and IP version 6. They all use the same message format. So from the point of view of the internal process, all of them are transmitting the same internal message format. It's the output formats, whether it's version 4 or version 6 or whatever. Those things are the only differences. We have a limit of maximum 5 requests in 3 seconds, and that's to deal with attacks, because we get a number of attacks. That limit is compatible with what's called the NTP burst mode, so that the burst mode will work on those with that configuration. Each server has a dynamic blacklist, which is a very important issue because we get a lot of users who attempt to disrupt the system. Now, let me talk a little bit about the authenticated NTP. It uses a standard NTP message plus a digital signature. The signature is computed on each request from the NTP message itself and from a secret key string. The secret key string uses a number of different hash methods. We support these 4 methods that I've shown. MD5 is the most common one. By far, almost all the users use MD5. A number of the others use the secure hash standard in the version 1 of the version 256 formats. I am working on an HMAC version, which turns out to be more difficult than I thought it was going to be. But I will hope in the next few weeks we will add support for HMAC SHA 256. We've had a number of requests from government agencies for supporting that signature format. The users must register and submit the IP address of the client, and the key that I send to them is, of course, unique to the user, and it's linked to the IP addresses, so it can't be shared. You can only use the key from the addresses which were registered at the time of the registration. The key distribution is a significant issue, of course, and we use out-of-band channels. There's a secure file transfer service, and we've also used the postal mail in the old days, although that's pretty slow now. We have 4 physical servers that support this service. There's one at each site, and all accept the same keys. Let me talk a little bit about the UT1 service. It is a standard server which is synchronized to UTC NIST, and the DUT1 offset is computed and added to every response. The DUT1 offset is computed from IERS Bulletin A with linear interpolation between daily values, so that when the NTP process receives a request, it looks up the IERS UT1 offset for today and the IERS UT1 offset for tomorrow, and it does a linear interpolation across them, and then that gets added to the NTP time service. We have 2 physical services that support this service. Now, let me just say one word about the design of the servers, because it is unusual. We have the control and supervision of the clock is done by a separate process, and the server process is a separate process. And that is a very important distinction between our services and many of the other NTP implementations, because many of the other NTP implementations combine the synchronization with the local 1PPS with the service to remote systems, and that means that the statistics are not optimum for either aspect. Making a separate process allows us to optimize the two processes based on the statistics of the various things. Now, I have a number of other slides which describe a number of the details for the system configuration and so on and so on. But I would stop at this point and entertain questions if there are any. I thank you for your attention.
Thank you, Judah. Is there any question for Judah? It's difficult for me to see hand raised, but it seems not. And I take the opportunity to say hello to everyone and to remind that if you please send me your presentation, it will be available on the working group webpage.
Sure, I was going to do that anyway, and the extra slides have information that maybe of interest for exactly how more details about how the system works. I'll send it to you directly. Thank you.
Yes, so I don't know if Marina is back. Yes, Marina is there. Please, we can go to the second speaker.
I'm sorry for being absent. I had to restart my computer. Have a reply to the question in chat? There is a Judah, did you see the question in chat?
I can't. We have a stack of set of one NTP servers at one place. UTC. No, the NTP servers, I guess, let me interpret the question because I don't completely see it. The question is whether our servers peer with each other, and the answer is no. Each server is synchronized to its local cesium clock, and the servers do not accept peer requests from anybody else, including their own systems. Each one of them has its own synchronization with respect to the local cesium clock. I trust that answers the question, but if it hasn't, please ask again or talk to me offline. Thank you.
The question from Michael Wouters.
Yes, Judah. Where does time of day come from then?
Well, the time of day has to be set when the systems are booted, and typically what happens is it's because all of the systems don't go down at one time. A system that gets rebooted gets its time from one of its friends, and then if that fails, the time comes from the local GPS receiver, which transmits. We use a U-Blocks receiver, and it sends a time of day message, but that's not normally needed. Once the time of day is set during the bootstrap process, the system just keeps track of the time by counting seconds. It compares itself with all the other servers to be sure that it hasn't lost a second, but it simply counts seconds. It counts essentially 1 PPS pulses from the local cesium clock.
Okay, thanks.
And the last question, I think it's the clarification on the previous one, is which model is more efficient for national time dissemination? The stack of NTP servers with UTC K1 PPS input, or geographically distributed Stratum 2 NTP servers?
Well, we use geographical distribution for two reasons. In the first place, the accuracy of NTP depends quite strongly on the network distance between the client and the server, and therefore geographical distribution tends to minimize the network distances. That's part one. Part two, it greatly improves redundancy. For example, just as a specific example, on this coming Saturday, the NIST Gaithersburg site will turn off the entire power for the entire site, and we'll simply lose everything. We'll have to do a complete cold start on Saturday. It just happens. And on the other hand, because we have geographical distribution, it'll hardly be noticed. The NTP Gaithersburg system will go down, but everything else will be okay. And the geographical distribution. So those are the two reasons why geographical distribution is very useful.
Let's thank Judah, everyone. And I invite you to follow up with Judah or because it's beneficial to everyone, maybe through the forum. You can post questions there. And the next presenter is Adam Danforth from MSL New Zealand. And I invite Adam, please, to share your screen.
And you can hear me okay?
Yes.
Cool. Okay. So thank you for giving me the opportunity to talk about network time in New Zealand. Probably from one scale to the other. I won't talk about all the slides because, as you know, they'll be available afterwards. But MSL is a relatively modest NMI. This is our campus, but it's the New Zealand's main campus for all of chemistry, physics, and engineering. So we're a small part of this, and we're a small NMI. As Judah mentioned, network delays are kind of important, both for NTP and for other network time protocols. But being a small lab, our history is probably like many labs, that we started NTP in a DIY kind of fashion. So we built our own timecode servers, and we built our own Linux boxes running a modified version of the NTP code with a custom ref clock driver that would read our timecodes. But of course, you know, as all of you probably know, NTP has moved on a lot since then to become pretty much mainstream infrastructure. And because of that, as a small lab, we've kind of had to sort of modify how we do things and move to using things that other people provide in a lot of ways. For example, we don't manage a lot of the network infrastructure ourselves. That's managed by our corporate IT. So they have geo-blocking, for example, on a firewall. Things like that. And kind of in that same vein of kind of choosing wisely what you can leverage off as a small lab, our network corporate services have done some work at the network level, segregating the networks. So rather than sort of historically having everything in one big network, we've now got network segregation for corporate services and lab services, and also for NTP. And so that's useful to us for configuring our network for NTP. So we've been fortunate, for example, to recently have to make a new lab. So along with the design of, you know, physically building a new lab in the environment, we've been able to think about the architecture that we want for our network connectivity for NTP. And for us, what that's meant is building on the network architecture that's provided at a corporate level. We've been able to segregate the network rather like other places do, so that we have our own lab virtual networks, but also networks for NTP service provision. And I guess in the same way that things have moved on, you know, you do all this wonderful design for architecture and you end up with a lab which looks pretty much, I imagine, like most other labs. It's full of stuff and full of cables. So we have network trunking up the top. I just realized you can see our new comb on either side of that picture on the left. But what we have in a practical way for NTP is on the right picture, you can see what we call our network cupboard. And so up the top, there are patch panels and things that we can configure our network as we need it, both for our lab operations, but for NTP. And then down below is the corporate IT side of things. So there are obviously interconnects between them, but we don't get to modify the corporate side of things, but we do have complete control, which is obviously quite useful to us and useful for providing NTP. And in the same way that kind of digital architecture has moved on, and we've had to sort of start using more commercial stuff in the same way equipment has. So whereas initially we built everything ourselves, and one of the reasons we did that obviously is people come to us for NTP because we're independent. We're all independent labs providing independent time. And so recently we've been able to find some NTP services from Alproma in Poland that have an interesting variant where they read time of day directly from the RS-232 on a clock. And so we've been able to use those to get the same independence that we were wanting, but in a commercial product. And recently, we've also been working with them because, as most of you probably do, we have offset generators to generate our actual UTC from the clocks. And so we discussed the idea that you could perform the same trick of effectively hacking into making a new ref clock driver that might talk to an offset generator. And that seems to be going okay for the last few months anyway. And kind of the last point, I guess, is to say again that now that NTP is such a mainstream thing, it's moved from being a research grade activity to sort of something that we provide as a service, and as a small lab, we need to be cognizant of how we can do that efficiently. And so whilst we still have our own monitoring, for example, that graph in the red there is our lab-based monitoring system that we've written and kept going over the years, and that's actually showing the operation of the NTP server that's connected to the auxiliary offset generator. But of course, nowadays, commercial NTP servers, or at least the ones we've got, also provide, direct monitoring access. So the graph below it is the loop stats, and over on the right there's NTPQ. So we would, traditionally have done all that ourselves on Linux. Now we can, if we're smart, we can get that from a commercial package. But of course, what you monitor and what you provide with your equipment and your architecture kind of comes down to what you can get, but also what you can't get. And so, for example, one of our main monitoring techniques is a fairly low overhead Python script, which basically generates emails for us by comparing against other available NMI NTP pools. And again, we've leveraged off some Python packages that do uncertainty analysis to kind of build in a way to use the network delays to see how bad our NTP system might be going. And that's really all I've got for my talk. This is one of those slides people put up saying, what are you going to do next? And for us, that's probably looking at PTP distribution nationwide, but it kind of illustrates the fact that NTP is now such a well-used tool of digital infrastructure that when you're a smallish kind of lab, you need to be thoughtful and mindful about how you do it and consider the things that you really need to work on and see if you can get them by using skills that are perhaps outside of your lab. So thank you, and I'm open to questions.
Thank you very much, Adam. And we have a few minutes for questions, so I invite people to raise their hands or post questions in the chat. We have a question in the chat.
I think this is for us, talking about traffic. So again, as a small lab, we basically don't do that ourselves. All of the traffic is managed for us in a sense before it gets to our lab by our corporate IT infrastructure. So they have geo-blocking, and they have blacklists of things. So in a sense, from our perspective, we don't have that problem so much. But in essence, that's because someone else is providing us that service. So the service still needs to be there.
Thank
I
you,
hope that
Adam.
answers the question. I hope that answers your question. If it doesn't, please come back to me.
Thank you. Other questions? Okay, I don't see any hands raised, so let's thank Adam again. Thank you very much. And our next speaker is Tetsuya Ido, and I congratulate the speaker so far being on schedule and even ahead of schedule. Thank you, greatly appreciate.
Okay. Can you see my screen? Oh. Can you see my screen?
Yes.
We can see.
Okay. All right. Then. Okay. So let me introduce our activity of NTP in NICT. So time dissemination using NTP protocol served by NICT. So this is a kind of the outline. So first, let me introduce our hardware NTP server. This was developed in mid 2000, around 2005, and we are using this. This is FPGA based, and so this can accommodate lots of the access. And we have a couple of the NTP service, public NTP. Anyone can access via internet, and the list line. This is one for company, and this is optical telephone device. This is a little bit. It's not a normal one, but only for Japan. But we developed this telephone line based NTP. So first, hardware NTP server. So in around 2005, we had great colleagues, and already part of them has retired, but they developed this great hardware server. This is the FPGA based and 1U server, and so FPGA based. So there's no OS and so on, and so this is really strong against the hacking and so on. And for sure, Stratum 1 server. And so this is the hardware server. So 1 million per access per day, per second. This is a large amount. Yes. And using this server, and now these servers are commercially available. We did the technology transfer to Japanese company, and then public NTP service. In our case, we are in Japan, and so you may know that Japan has lots of the natural disaster, for instance, earthquake and so on. So for this NTP service, we are doing the service from headquarters, which is in the Tokyo, and also the other one, we have the Kobe service station. This is the western part in Japan, and then and there are a couple of servers in each stations, and so currently the access per day is 10 billion, and this kind of the way we have the good redundancy, and so this is an NTP server. So basically, in principle, this is the best effort service, but we seldom stop this service. And this is the number of access per day, and so now still it is going up, and thanks to the FPGA based server, the server still has the room to accommodate more accesses. And this is a number, and so basically Japan and China is two major countries which access to our NTP service public. But as I said, the server is fine, but now we have a little bit problem with the bandwidth of the NICT Internet Exchange, the bandwidth of the line. It's not the NTP server. So this could be a problem. So we are now wondering to move the server to some more internet exchange or something, then we can reduce the load at the line between the NICT and exchange. And this is a public NTP, so that anyone can access. And also we have the list line NTP. In this case, some companies can set their own line to our headquarters. And in this case, this is the service for the company, and so we cannot disclose so much information. But this is only available at the headquarters. So I think this case we want to, in future, we'd like to have that one also served in Kobe for the redundancy and for the resilient view. And another thing, let me introduce, this is optical telephone JJY. So JJY, this is a call sign of our space long wave standard time dissemination way. And so this is saying that using kind of the time reporting function using telephone. And now in Japan, the telephone system is transferring from analog system to the optical system. And so actually in mid-1990, we started the analog telephone JJY. So the kind of the JJY service using telephone. And now this service is transferred from analog to the optical. So this optical telephone JJY service, this is a NTP using the dial-up optical telephone call. In this case, this is a dial-up. So from 1 to 1. And also this line is not in the internet. It is a line of the communication company. In our case, this is the NTT. And so this means that the line is separated from internet and secure. And also the good thing is much cheaper than list line. List line company has to pay much money to the communication company for the line, a dedicated line. But in this case, this is a telephone line, and so just a telephone view. But we are saying that the high frequency access is prohibited. So one customer can access only 24 times per day, so once per hour. And in this case, here we have the failover strategy, availability, integrity. So this means for sure we have the multiple servers in headquarters and also Kobe substations. And actually, as I said, in mid-1990, we started the service of analog telephone JJY. This is based on the analog modem. So this does not provide us the NTP protocol. On the other hand, around 2010, we researched and developed optical telephone JJY system. In this case, the system can provide us the NTP protocol, so which is really nice for the computer network. And so now, and these registered accounts are now going up and up. And you can see here that we are asking customers to move from analog telephone JJY to the optical telephone JJY. And next March, we will stop this analog telephone JJY to this optical one. In this case, so as I said, NTT communication company, optical telephone line comes to the headquarters. And here, the NTT has a service for the data connect. And sorry, this is Japanese still. Data connect that allows the one point-to-point point-to-point internet protocol. And so using this, the company can access to UTC and ICT using a telephone line, which is separated from the internet. So some companies don't want to touch the internet, but they can get the UTC and ICT using NTP protocol. Yes. So here I wrote here that the analog JJY or analog telephone JJY had a problem because the telephone line moved to the digital or optical. Then the two-way strategy does not work anymore. So the accuracy of the analog JJY has decreased, has deteriorated. But this optical telephone line, they can manage such non-identical pathways, and this system can has the accuracy of the 0.1 millisecond or less. Yes. So these are the NTP services provided from NICT. That's all. Thank you very much.
Thank you very much, Tetsuya. And we already have 2 questions in the chat.
Okay.
And the first one is NTP server maximum throughput is measured at Ethernet port level or device level?
Level or device. This is basically what they mean. So I think this is a Ethernet port level. So I think NTP protocol does not have so much information, and so I think these two are almost identical. Iwama-san, do you know this? If there is a difference of the capacity on the these two?
Yes. In this case, NTP is only a port level, but one port have 2 IP addresses, and we use totally 1 million access per second for one machine. But one machine have 2 IP address and only one port use.
As a machine, we have the 1 million per, yes.
So I think that answered the second half of the question. The maximum capacity, it was 1 million calls, the device can handle, and I think you mentioned was 1 million calls per second. There is another question in chat, and then we have Joseph Ashkar hands up. So the question 2 is, as you mentioned, NTP service and dial-up optical telephone call, please share the business model for commercial NTP services, authentic NTP services to specific customers, if you can.
So I did not say, but we don't charge the customers for this NTP service. That is also for the list line. So I would say we don't have any business model at this point because we don't charge from the company for this NTP service. So the customers just need to pay for the, for instance, for the optical telephone line. Then in this, they have the only telephone bill, and also list line they have to pay only for the communication company. We don't get any money from the customers.
Thank you, Tetsuya.
Yeah.
Joseph?
Hello everyone. Okay, thank you, Marina. So thank you, Aido, for the presentation. I have a comment or a question concerning optical telephone JJY. I find this possibility very interesting, and as far as far as I understood, you show that traceability to UTC and ICT is ensured. So what is the level of performance achieved with this technique, or what you are allowed to provide to users? Performance, technical performance, yeah.
So say it again. So the performance level of the accuracy, or
yeah,
optical telephone GY. Oh, yeah. So optical telephone GY. So in this case, we are saying that the accuracy is 0.1 microsecond, 0.1 millisecond, so 100 microsecond. And we checked that as long as it is inside Japan, we can get such precision, accuracy.
Okay, excellent, thank you.
Yeah.
Thank you, Tetsuya. Yeah. And we have probably a question from Patrizia in the chat.
Yeah.
How do you keep the two sides synchronized?
Oh, for this Tokyo and Kobe synchronization, basically we use GNSS time transfer currently, and so the two clocks, UTC NICT and the clock at Kobe, these are synchronized in at least 20 nanosecond or something. Yeah, so we think that for this NTP service, this is good enough.
Thank you.
Thank you, Tetsuya. There is another question in the chat, and I'm not sure if it's directed at Tetsuya, at you, at everyone here, to all NMIs. Is there a lab that offers a commercial service to specific customers? If so, primary. I don't think we have time right now to survey all the NMIs. So Tetsuya, maybe you can answer just for Japan, just for NICT.
Oh. For just the NICT, as I said, at this point, we don't have any charged service for the time. Basically, all are free, and so but the customers have to pay to access our lab, either in list line or telephone, or yes, that's it. So unfortunately, we don't have any such business model at this point.
Well, thank you, Tetsuya. Thank you, everyone who asked questions. We'll have to move to the next presenter. I see that there are still questions coming up in the chat. You can answer in the chat, or you can answer in the at the forum after the presentation. Our next presenter is Michael Waters from NMIA. Michael, please share your screen.
Thanks, Marina. Oops. Right. Hello, everyone. The NMIA NTP service has two distinctive features. First, it's distributed. We have servers in Sydney, our main site, Melbourne, Adelaide, and Perth. Each of the remote servers has a local clock, a GPSDO, a rubidium, or a cesium in the case of our Melbourne server, that's linked back to our UTC Australia in Sydney via a GPS Common View link. The remote servers are intended to provide better service to local users. The round trip time for an NTP query, for example, from Perth to Sydney is about 60 milliseconds. So a local user of our Perth NTP server hopefully benefits from the shorter network path. The second feature of our NTP service is that, unlike everyone else, I think, our servers are closed access. A policy which was adopted 19 years ago, actually, in response to misuse of our servers, which was causing significant and exponentially increasing network traffic. So prospective users have to contact us first and tell us the address or the block of addresses that they'll be accessing our server from. We don't usually say no to anyone, but they have to tell us that they're going to use it. We suggest users register no more than 3 addresses and use these as Stratum 2 servers for their own network. Currently, the number of active users is only about 300 users, but this includes internet service providers, telecoms companies, universities, financial institutions, and so on. So I guess the benefit of doing this is we know exactly who's using our service, and we can point to, you know, the benefit of our NTP service. And the other, I guess the other point I'd make is that, you know, although the number of users is small, the fan out can be quite large. So, you know, a university may be distributing time to 10,000 systems on their local campus. The image I'm showing here is a live display. Well, it's not live now, but it's a screenshot of a live display of traffic to our servers, which is possible because we know who our users are and roughly where they are. And of course, the traffic is not terribly large. We're only getting about 100 packets a second to those 4 servers in total. So hardware. So our remote servers are built on our standard time transfer system. This includes 3 GNSS receivers, a GPS receiver, which is used for the time transfer function, a Beidou one, and a GLONASS one. The idea being that we intercompare these 3 receivers in the same way that you compare a number of atomic clocks to check that each is working correctly or to detect faults. The oscillator in these things used to be a rubidium, but we've started using GPSDOs instead because rubidiums have turned out, well, have proved to be the least reliable component in the system. Local systems, that is ones that we run at our Sydney site, are a bit simpler. So these just tend to be industrial rack mount servers, which have proved to be very reliable. We can use, you know, multiple PPS inputs with these via some custom hardware, which converts a PPS signal to a serial code, and you need a custom ref clock driver for NTPD. So we're still sort of following that path that Adam said that they initially did, but are no longer going along. So we've always aimed for a diversity of time of day sources as inputs to our NTP systems. In the time transfer system shown here, time of day is coming from this GPS receiver and from the GLONASS receiver. For our Sydney and Melbourne systems, we also have time code generators and time of day available from 5071s as well, via, again, another custom ref clock driver for NTPD. So software, okay, it's all built on top of Linux. We've always used Linux on our NTP servers, mostly because it gives us full command line control of a remote system. This means that we don't have to writing user interface software and so on, which is even more significant considering the other functions that we've tacked onto these things like the GPS common view for the remote systems. Unix-like operating systems are also generally the best for using NTPD anyway. The flexibility of full command line control, of course, is a bit of a security issue as well, and I'll comment on that in the next slide. We use NTPD for NTP service. We've written a number of custom ref clock drivers like the HP 5071, as I said, and then a few other GNSS receivers that NTPD does not support, but we have been using for time transfer. There are also some other minor customizations, including being able to control leap second announcements. We ran into a problem a while ago where we started announcing it according to the NTP protocol, i.e. more than 1 day early, but this actually caused problems for some NTP clients which immediately applied leap seconds because they didn't know about, well, they didn't follow the recommended times for applying leap seconds. We're also testing Crony which is another NTP implementation for general use. Since this offers a more convenient authenticated NTP than does NTPD. Like NIST, we do offer authenticated NTP just by symmetric MD5 keys though only. But the disadvantage of offering secure NTP via Crony is that, of course, you have to use SSL certificates. So there's a bit of a maintenance issue there. And then sitting at the top of this all is a bunch of custom software. You know, since we're using an access control list, we're just using NTPD's own access control list rather than implementing it at a firewall. We have to have ways, you know, to sort of centrally send out changes and then automatically implement them. And we do a bunch of other things like traffic logging too. This can be useful. Sometimes we've had requests from our users to provide some evidence that their boxes have been synchronizing to our servers, or at least making a request anyway. We don't know whether they get a reply. And so these records have been useful to give them information about that. So I'll say a little bit about security, I suppose. So we're running these on general purpose Linux servers. They're not locked down embedded operating systems like you would find on a commercial NTP appliance. What was I going to say? Sorry. So a commercial NTP device will typically have very tightly defined configurability and use a read-only file system for its critical software. And you can, you know, only update the whole system as an image rather than updating individual components. Our NTP servers are particularly exposed because they sit outside of our corporate network on dedicated connections at Sydney and Melbourne, but on the premises of third parties like data centers, for example, for our Adelaide server. So, you know, if you bring up a machine on the internet, have the SSH port open, for instance, you'll start to see it be attacked within about 20 minutes or so. So how do we manage security? Well, there's nothing really magic, but first of all, we build the systems very minimally. There's only the software that we need on them. That's, of course, one of the advantages of Linux. You don't have to import a whole ecosystem. You can just build a very minimal system. There are certainly no superfluous network services running on it, like email. Then we just have a host-based firewall, which restricts command line access really to just 2 IPs from within our own secure network. And then, you know, the various automated data transfers are all, data transfers and maintenance commands like updating access control lists are all done via restricted shell, where, you know, you're only restricted to issuing 2 commands in effect when you make when you do a login. I just check the time. For monitoring, so we have, you know, a continuous monitoring process that looks at connectivity and ref clock status. We get email alarms about that. Also collecting lots of logs from the system each day, from which we generate daily and weekly reports, which are received via email. And then we're looking at things like our users, how many are active, whether we're getting unauthorized queries from somebody. So even though it's a restricted, you know, a closed service, there's leakage, somebody copies a configuration file, not really understanding that they need to have their IPs registered. We have sort of tried to track down people in the past, but we don't really bother anymore. That is, track down unauthorized users, that is. And of course, you know, just the usual things like traffic stats, second status, and then the data related to, you know, the operation of the system, like the GPS common view data and measurements of the actual system time. We also have another continuous monitoring process that feeds into a dashboard that sort of gives us a general view of all of our timing systems, but that one's more just for a pretty display than practical information. The clock used by NTPD to get timestamps is the Linux kernel clock, a software clock that's steered by NTPD as well. To complete the traceability chain, we'd like to know the offset between the local reference clock, like a cesium, and the Linux software clock. We do this by generating a 1 PPS signal on a digital I/O port on the single board computer that's in these systems via software that's running under Linux, and then just measuring the difference with respect to the time interval counter. You can see some typical data below where it's, you can see a jitter of a couple of microseconds and then an offset of about 5 microseconds or so. This generally agrees with NTPD's own records to within about 10 microseconds or so, but you do see steps that aren't evident in the NTPD data that are probably due to changing interrupt priorities in the operating system. So with for the remote systems, these measurements are combined with the GPS common view data to complete the traceability chain. And we report these measurements on our one of our web servers, just as a summarized each day as a maximum offset. So there are a few users, for instance, who use this data for checking, well, they use our NTP servers for checking stopwatches, and then this data completes the traceability chain for them. Right, so I see that I have just a couple of minutes left. And this is really just a project we're working on with a local university to improve NTP distribution and health monitoring. So the model here is really what NTPD, well, partly what NTPD started with, as in you had top level NTP servers, and then you had a hierarchy of NTP servers below that that did the grunt work of distributing time. But of course, what's happened is everyone just points their servers at a stratum 1. We have a layer in the outer core of enhanced stratum 2 NTP servers, and in the inner core, stratum 1s, and then at the center of this, the trust node, which does monitoring via talking to both the stratum 1s and the stratum 2s, and it gives information to the stratum 2s about the health of these systems. So a key part of this is a large distributed group of stratum 2 NTP servers providing public NTP service using improved synchronization algorithms, and in particular better handling of network path asymmetries. That requires an initial measurement of network asymmetry to kickstart things. So this is actually running. There's an inner core consisting of our NTP servers, and there are outer core nodes in ARNet, that's the Australian Universities Network Operator, in their points of presence in Brisbane, Melbourne, Perth and Sydney. There's a very detailed sort of dashboard for visualizing all of this in action. So the reason we're doing this is that we really want, it would be nice to start again to distribute time to the public as opposed to having the closed access service. And it would be, the way we see it is doing it via participation in this, because we wouldn't be necessarily running this bit. We wouldn't necessarily be all of the servers that are in this inner core. And we wouldn't necessarily be running these either, but we would be part of this ecosystem. So the general comment I'd like to make before I close is that our NTP service has been running for about 25 years. Some of the decisions we've made reflect the state of things 20 or more years ago and may not be what we decide to do today. We're currently doing a rethink of some things, particularly in the context of maintainability of our service. Thank you for listening, and I don't think I really have any time for questions according to the timetable. So if you do have any questions, you can just email me. Thank you.
Thank you, Michael. Yes, unfortunately, we have no time left for questions. There are a few questions directed to you in the chat. Please, if you can, provide the answers in the chat so many people can see them. There are also questions to all NMIs, and I plan to post these questions on our forum so people can post answers that also will be visible to everyone. And I invite you to use this resource. So we will switch to the next presenter right now. The next person is Nir Chabani from Focus Telecom on behalf of INPL. Nir, please share your screen.
Yes. Hi, everyone. Just a second, I'm sharing the screen. Can you see it?
No.
Marina, can you see this now?
Yes, I see it.
Okay.
Okay, Nadia, please go ahead.
Yes, yes. I would like to say information about the Israeli National Time. The National Time is formed and stored on the basis of a high-performance seism clock, and the international key comparison are performed using modern TTS-5 system with ability to precise point positioning, and the standard deviation of the measurement results of comparison of the scale, national scale against UTC is only 70 picoseconds in one set of measurements. The next slide, please. And the difference between the national time and the UTC during 8 months from October 2022 until May 2023 was in the range of plus minus 20 nanoseconds only, and such accuracy is quite sufficient for the national infrastructure, and the problem is to transmit such high accuracy to the customers without interference and without disturbances. The National Physical Laboratory of Israel, as a leading laboratory, together with its partner, the telecommunication company Focus Telecom, conducts research on the development of the national time network based on fiber optics, and protected for cyber attacks, and protected for attack on satellite signal. Mr. Nir Chobani will present the structure of INPL time dissemination. Please,
Thank you, Nadia.
Please, Nir.
So hi guys, what we are going to say today, we are going to speak about a couple of topics, and especially show you the time dissemination of INPL. What bothers us is that we had a very great reference based on 4 cesium inside INPL, but it was only inside INPL and we didn't share it. So now we see all across the world that people are going for time dissemination or time distribution from the core sites of the national laboratories. So what we have done and what we are going to display now is, first of all, we are depending on GNSS as a sole reference. This is what we are doing today. And we are we know very well now that GNSS is not that reliable. We cannot only rely only on GNSS because it's very easy to spoof or jam the signal. So what we are going to see is the alternative that we suggest and the use of INPL as a reference, a secondary reference to the GNSS. What we are going to cover as well is the EPRTC G8272.1 that we implement in the INPL laboratory. We will discuss the INPL advantages. We will display the dissemination architecture. We will share with you the test bed at customer side that we did and the accuracy measurements that we did from the customer side. And looking forward, we already conducted a couple of measurements based on fiber optic, and we have great results to share with you. So today, most of the organization have their sync servers, and it's depending ultimately on GPS. Once you don't have GPS, you enter into holdover and you have a time drift, and it's depend on the accuracy of your oscillator that you have inside. It will conclude how long you will be able to serve your applications and your business needs. What we decided to do is to use INPL infrastructure and as a second reference to the GPS. And using the INPL, we needed to organize two things. First of all, to make sure that we can deliver time from INPL. And the second thing was how to distribute it further to the customer side. So let me introduce, maybe all of you already know the EPRTC G8272.1, that when we use both PRTC, primary reference time clock, along with a very stable frequency of the cesium, then we can receive the EPRTC that according to the specs supposed to be accurate 30 nano to UTC. But the most important thing is that the holdover of this EPRTC is 100 nano for 2 weeks, 14 days, and only drift of 100 nano. We cannot get it without any oscillator today. So INPL have today a very stable clock that is being stabilized by the 10 mega reference and can perform a holdover of 100 nanosecond for 40 days. The next challenge was how to distribute this accurate clock. Now, if we look at the advantages of EPRTC, so as I mentioned, the holdover is better than 100 nano for 14 days, and we are speaking today under discussion of EPRTC-B, which will be 100 nanosecond for 80 days. So it will be even much better. And the third reason is INPL is constantly reporting to BIPM. So we also have an external reference that in case someone tries to spoof our time, we will be able to alert it due to the connection to BIPM. Now, what we did, we took a regular IP VPN from the local operator, network operator, telecom operator in Israel, and we asked an IP VPN between the customer site and the national laboratory. Then we used the PTP protocol, 1588v2, in order to distribute the time from the EPRTC towards the customer sync server. Now, the sync server at customer side has a primary reference of GPS. Now, what we did, we installed another reference and we compared the 1 PPS from the customer sync server based on PTP. We disconnected the GPS from this unit to the GPS reference 1 PPS. And before adding this resiliency, the customer had only sole reference based on GPS. And after adding the resiliency, the customer has the first reference as GPS, but once he loses reference, he has a secondary reference that coming directly from INPL via PTP with a great holdover. And if we are looking at the graphs, what is going to happen if we are not using, before adding this resiliency to GPS jamming spoofing, we see that the time drift with the standard oscillator was 240 microseconds after approximately 3 days. But once when we connected to INPL, the customer does not have this drift anymore because he's synchronizing with the PTP, via PTP from the EPRTC based on INPL. And the measurement that we are conducting from the testbed that we have seen in the previous slide, we've been able to see that we get a time error of plus minus 150 nanoseconds between the live sky GPS and the PTP that coming from the INPL. This measurement was taken at customer site. And the MTI for this is showing under 300 nanoseconds. So even the MTI is good. So for customer who using needs of microseconds, even microsecond, not only millisecond, it's more than enough to have this architecture. Now, another thing that when we are looking forward, how to distribute it furthermore, we conducted some tests using a fiber optic from the same EPRTC. We've been trying to provide PTP in time to remote locations. So one of the remote location was 64 kilometers from us. This is a remote site B. And the second one on the test, and it was a live test, was 54 kilometers. So on this, in this scenario, we use the EPRTC in the INPL lab, and then we connected via bidirectional SFPs in order to overcome some delay propagation that could be through the different lambda. And we use a single fiber to each of the sites. And if we are going to the measurements, we can see that on 24 hours on site A, we got 7.4 stable, 7.4 nanosecond stable measurement for 24 hours. And on site B, we got even better, 4.28 nanoseconds for 24 hours. And this architecture, the idea is to connect some centralized POP of telecommunication to INPL, and they will help us distribute to the customers and reduce the dependency that we have today on GPS, even in higher application that demands higher accuracy, such on the nanoseconds level. Thank you very much.
Thank you very much, Nadia and Nir. Interesting presentation. See, we have a couple of minutes. I don't see questions in the chat. If anyone has a question, please raise your hand. Well, I don't see any hands raised. I want to thank, oh, sorry, there is a question that came up. What profile configuration for PTP are you using? I think that's
that is, we use Telecom 2008, for example, Unicast. And in the second one with the fiber optic, we use ITU G872.5.1. It was a multicast layer 2.
Thank you very much, Nir. If there are no more questions, I would like to thank Nir and Nadia again for their presentation. And the next speaker is Albin from government. I invite Albin to share his screen.
Okay. Can you see the screen?
Yes.
Okay. Hello, I'm Albin Czubla from Center of Measures GUM in Poland. And thank you for the opportunity to share our experience in network and dissemination services for UTCPL. So at GUM, at Center of Measures, we have 2 atomic clocks. So we have at GUM currently 6 NTP servers, and the last NTP servers were purchased this year. So all NTP servers are synchronized by 1 PPS to UTCPL, and time of day information is taken from CSIM clocks and from the other NTP servers in our group. And currently we anticipate a bigger loading of NTP connections, so we are prepared to use load balancers to share traffic to the different NTP servers group. So also we have PTP servers. Currently we have 5 PTP servers which offer totally 20 SFP ports with 1 gigabit Ethernet, and every PTP server is synchronized by 1 PPS and 10 megahertz directly steered from UTCPL, and the day of time is taken from NTP servers. So in that way, we would like to offer to establish dedicated PTP connections over the fiber telecom network. And this is a requirement only to have its own PTP receiver and provide an optical fiber link to access to our institute and to access to the pair of SFP transceivers. And we also can calibrate NTP or PTP connections with the usage of calibrate and PTP NTP calibration tester. So this was possible within the project eTime PL. This is a trusted and reliable legal time dissemination system in the territory of Poland. However, this is only one part to strengthen the hardware base of legal time dissemination. The next objective of the project are also to build new sub-services for better usage of an NTP, or for better trusted to NTP servers used in public and private domains. So we also built a web platform which gives opportunity to monitor both public NTP servers, which are linked directly to our servers, and also for private NTP servers, which are in private local network. And in the second case, this is required to install a special software, which is for monitoring, which is in fact an NTP daemon in a non-select mode, which connects directly locally to the private NTP servers, and next send and next compare its time to an NTP servers at GUM. So it is available for registered users and with authentication with a symmetric key. And all data are collected at GUM servers, and there are possible creation of graphs and reports. So this is the standard parameters as clock offset, run trip delay, jitter, etc. So, and next, we also offer the sub-service to monitor real-time clock in PPC computers via simplified the network time protocol. So it requires only to download and install a special applications software with predefined addresses of NTP servers for UTCPL, and all the data and reports are located and generated locally at the computer. Also, we think about making more facilitate to use time taken from NTP servers, and we also construct, create widgets with time taken from NTP servers of GUM for small widget for websites, and which can also in full screen operated. So as such, widget also can be used for mobile phones or in the different institutions and public places to display local time at monitors. So, and the final extra issue for consideration is that some media operators request not for UTC PL time transmitted by NTP, but for local time. And I only guess that the reason are the simplified electronics used in some smart meters. However, because of a high risk of misunderstanding, we not decide to run such service. So thank you very much for your attention.
Thank you very much, Albin, for your presentation. I hear in the chat a question. What's the policy of service level agreement in authentic NTP service, and how would you ensure maximum uptime for the time service?
Could you repeat? I tried to find the question.
It's the last, it should be the last post to everyone. What is the policy of service level agreement in authentic NTP service? And how would you ensure maximum uptime for this time service?
If I could understand the question, the exchange of symmetric key is generated in a web platform. So if the symmetric key is dedicated to IP address, and the maximum uptime for time service, it depends on the user. So we don't define. So we assume that the difference will be not bigger than 1 second. However, we don't define any limit for the user. So if anybody monitors its own NTP servers, could observe the maximum difference being a half of a round trip delay for the during monitoring an NTP server.
Thank you, Albin. I hope that answers the question. Are there any other questions? I invite people to raise their hands or post the questions in the forum. Sorry, in the chat. Okay, I don't see any more questions. I want to thank Albin for his presentation. Before I invite the next speaker, Claudia from Colombia, I want to point out that there were a lot of questions in the chat asking whether we can continue the discussion online following this meeting. And yes, absolutely we can. And I would encourage all of you to do so. And I would encourage you to use the TAI Working Group TAI forum. Patricia just posted an instruction how to register to get access to the forum. If you don't have until now, please read the instructions in the chat. Register for the forum. I am trying to create, will create after the meeting a new thread dedicated specifically to this meeting. It will be in the meeting and the meetings under the meetings headline. And I'll try to post the questions there from the chat. And if you don't see your question, please add your own questions or comments and answers. And with that, I invite Claudia, please, to share your screen. Thank you.
Thank you, Marina. Can you see my screen?
Yes.
Okay. Okay, hi everyone. I am Fernanda Rodriguez from INM of Colombia, and it's a pleasure for me to present the way how we disseminate the legal time on internet using the network time protocol in our country. Well, this is our time and frequency laboratory, and it has the function to generate, maintain, coordinate, and disseminate the legal time in Colombia. It was mandated by the government through a presidential decree. Colombia participates in the realization of the Coordinated Universal Time, UTC, since 2017, and contributing its clock data to the BIPM, and also participate in the same time scale since 2007. And the laboratory has a session clock. You can see in the white rack, and a time standard and GNSS receivers, NTP servers, and auxiliary instruments in order to fulfill its function. Well, the network infrastructure for dissemination, the legal time, is composed by different systems or devices that allow the flow of information with a strong level of security. Each of them has a responsibles. And firstly, we have the NTP server at the laboratory. That is the instrument in charge of providing the timestamp and sending on the local area network to the virtual server. This virtual server is in charge of provide the public domain in order to the clients consume the time service. The switch core route the information to the firewall and NTDOs, wherever the security is warranted, and send NTP response via internet to the client. The security system protects the INM network, identifying external attacks like distributed denial of service or unauthorized access. As you can see, in this case, the information technology and technological development Office has the responsibility to maintain the security infrastructure and expose the time service to the internet. The INM of Colombia provides two types of services. One of them is free and the other one is paid. Firstly, I'm going to talk about the free service. The legal time free service has three modes to access. The first one is the time service using the NTP protocol. For at least 10 years, this access mode was provided by public IP, which responds the NTP requests and the web clock. These requirements demand resources and a high internet bandwidth, and the risk of the fall of the web page was critical. For these reasons, during the last 5 months, the Information Technology and Technological Development Office and the Time and Frequency Laboratory, in addition with the Ministry of Information Technology and Communications, have been working on the update of the legal time service. Then the NMI implemented 2 web domains. The first one is ntp1.inm.gov.co, is on-premise service, and like a backup, ntp2.inm.gov.co in a cloud that provide the web page with a web clock. And the other mode is voice signal via telephone, dialing the phone number shown in the slide. This is the free service schema, and we have a session clock that provides UTC INM time scale, and this clock is found within a real-time intercomparison using the UTC time scale and monitoring through the Inter-American Metrology System time scale. A PPS signal is used to discipline the NTP server oscillator, and the NTP server is, the brand is Microsemi, that is the Stratum 1. Then we have a server in our network infrastructure, like on premise. This server is configured to request the timestamp to the NTP server every second, and this is Stratum 2. Finally, we have 2 servers, a virtual servers in an on-premise infrastructure and a server in a cloud infrastructure as a backup. The virtual server requests to the timestamp to the previous server every minute and disseminate a timestamp via NTP protocol using the domain ntp1.inm.gov.co. Also, we have a server in the cloud as a backup, which requests the timestamp to the previous server and disseminate the legal time in 2 ways. The timestamp via NTP protocol using the domain ntp2.inm.gov.co, and the other is the web clock to display the time to the citizens. Approximately, we have 1,000 of NTP requests every minute. And now I'm going to talk about the paid service. In the last years, we identified that the free service had improvement opportunities. The INM identified the public IP limitations. It was before the new implementation of free service that may arise due to the limit number of connections supported, the vulnerability to hacker attacks, and it's not possible to monitor the clients who are using the legal time. Therefore, improvement opportunities were identified to ensure the level of access, like a stratum, and continuity of the connection services with availability, checking the client status, and improve security access through an exclusive IP address, consolidating the new service category. This is the paid service schema, and we have a session clock that provides UTC INM timescale. A 1 PPS signal is used to discipline the NTP server, and that is in stratum 1. And then we have a virtual server in our network infrastructure, and this server is configured to request the timestamp to the NTP server every minute. This is in stratum 2, and disseminate the timestamp via NTP protocol using an exclusive IP address for this service. We developed a measurement software on Java programming language that runs on Windows, Linux, or Macintosh operative systems. And this application requests the NTP packet from the INM virtual server every 60 seconds and captures the NTP timestamp for both the client server and the INM virtual server in order to record the offsets and the delay measurements. These applications runs on the client server that creates a local database, and then the connection IP address is identified in the client, authenticated to allow it to enter in the INM network. The application has the option to establish 2 types of connections to the virtual server. The first one is through a virtual private network, where the client previously performs their security system and access with the IT office. And the second, it's done through an exclusive public IP address. And the measurement interval is set to 60 seconds. Immediately, the application establishes the connection with the INM virtual server, and in order to get the NTP packet by request. The NTP packet received has 4 timestamps, which are stored in a local database, and then the offset and the delay are obtained using the equations. The application's interface plots the offset that is updated every 60 seconds, and when the application counts 1,440 measurements, it exports the data in a CSV file and automatically sent to the INM email service. And at the end of the month, we deliver a measurement report. At this moment, we don't have any client for this service because we don't have a law or a decree by the government. And for this reason, it was complicated obligate the clients to pay this service. And it was all. Thank you.
Thank you very much, Claudia. And we have a few questions. So the first one, for your paid service, do you monitoring certificate or report with uncertainty?
Where it was the question of the buyer.
It was the question whether you provide monitoring certificate with uncertainty, the certificate report with uncertainty to the client.
And I read the questions, the question
It was
of
a question from Frank Calabrese at 9:36. Sorry, on my Ottawa time.
36. Okay. Yes. If in the question of the free case NTP service, how will you handle how requests and how many NTP servers are located for free NTP service as micro semi NTP server have around?
So that's, I think that question was, Claudia, I think that question was for everyone. What about the next one? Look at the next one.
Okay. For you per paid service, do you provide a monitoring certificate or report? Okay. We provide a report because a calibration certificate is not used because the synchronization is like a adjustment, and for this reason we don't say there is a calibration certificate, and maybe is most relevant and report of the measurements, and the uncertainty is related to the repairability of the measurements in the case of the offset.
Thank you. There is another question, the next one. In case of virtual Stratum 2 server, what's the accuracy of the server and the time reference configuration?
Okay, we configure the pool in the NTP protocol. And for this reason, the synchronization of the virtual server is done every second. And in this case, we are ensure that the accuracy is with a high level and in the order of milliseconds.
Thank you. We still have a couple of minutes, so just quickly, how many servers are used to provide paid services? And please share your business model.
Okay, we have 2 servers. One is the virtual server and the other in a cloud servers. And the business model is paid for the use of the application and the IP address and the exclusive IP address. But is a low cost, but the companies don't pay at this moment.
Thank you, Claudia. There are a couple of more questions, but I wonder if we can continue, if Claudia can continue this discussion via chat, so we can transition to the next and last presentation for today. And thank you, Claudia, very much. I'm very excited about how much live discussion we have in the chat. So thank you all for your active listening. Our last presentation today will be from Andrei Sharbanov from NRC. Andrei, please share your screen.
Thank you, Marina. Can everyone hear and see the screen?
Yes.
Thank you. My name is André Charbonneau. I work at the NRC Metrology Frequency and Time Group. Thank you for the opportunity to present today. And my talk will talk about leveraging free and open source solutions for automation and monitoring of NTP servers. The NRC operates two sets of Stratum 1 NTP servers at two different locations operating on different networks, 3 Stratum 1 servers at our primary site and 3 Stratum 1 servers at our secondary backup site. The diagram here shows the overall architecture of the Stratum 1 NTP service at the Time Lab in Ottawa. At the top of the diagram, we have 3 cesium frequency standards that provide a 5 MHz signal to 3 leech clock drivers. The leech clock drivers also take the lab's UTC NRC PPS signal as input. The time of day is manually entered on each of the clock drivers, which generates a time code that is fed through a supervisor unit. The supervisor unit continuously monitors the time code and discards outliers if detected. Then the interface box combines the timecode data stream with the 1 PPS signal, which is then fed to each Stratum 1 server via its serial port. A similar setup is replicated at our backup site for redundancy and business continuity. The NRC Stratum 2 servers are also deployed at both the primary and secondary site. As shown on this diagram, each Stratum 2 server uses all 3 Stratum 1 servers at that location as reference. The general public then configures their NTP client using either a round-robin DNS entry, which contains the 4 Stratum 2 servers, or they can point directly to each Stratum 2 server by hostname or IP address. Not shown on this diagram are spare NTP servers that are powered up and ready to be added to the Stratum 2 pool in case of replacement or additional servers are needed. This diagram also shows the monitoring component we have deployed at NRC. This allows us to monitor the performance of the NRC NTP servers and get notifications when something is abnormal. We will talk about NTP monitoring in more details later in this presentation. As with any piece of IT equipment, the NTP servers are subject to regular system administration tasks, such as regular OS updates or new software installation. NTP configuration will most likely need to be changed occasionally in the case of an upstream reference change, for example, or deployment of new NTP authentication keys. With 1 or 2 NTP servers, doing this manually should not be a problem, and this is how we have been managing the NRC time servers for several years. But when the fleet of NTP servers grow, these repetitive tasks take considerable amount of time and resources. Also, when the workload is shared between group members, some inconsistencies on how these sysadmin tasks are performed are likely to occur. Can we automate some of these tasks without disrupting the current setup and configuration of the NTP servers? Well, the answer is yes. Turns out there are many options available to help with IT automation. One such solution is called Ansible, and that is the one we adopted at NRC for our NTP servers. Ansible, first released in 2012, is a suite of command line tools for IT automation, which can be used for provisioning, configuration management, and application deployment. Some nice features of Ansible's design are that it does not require any special software agent component to be installed and running on the managed systems. It uses OpenSSH for secure communication to the managed nodes, and it supports both Linux and Windows. Ansible has been acquired by Red Hat some years ago, but still provides a community edition that is free and open source. When you use Ansible to manage your servers, you first need a control node, which is shown on the left in this picture. This is the system that will have the Ansible software installed. On the control node, you list the systems you like to manage in an inventory file. In our case, these are the NTP servers. Then the tasks that need to be performed on the managed nodes are written in what is called an Ansible playbook, using a markup language that is simple and clearly describes the details of each task. The system administrator then invokes the Ansible tools, which will read the inventory and playbook files and connect securely to each managed nodes and perform the task required to bring the system to the desired final state. When a new NTP server is added to the pool, the Ansible tool can be run again, and it will bring this new NTP server to the same state as the other systems in the group of managed nodes. Ansible enforces consistency in your pool of NTP servers. Let's look at a concrete example. Deploying new NTP authentication keys to NTP servers can become a time-consuming process as the number of NTP servers grow. Doing this manually also increases the chance of user error during this process. Using Ansible, you can write the playbook to copy the NTP keys to each of the NTP servers and then ensure that these keys are activated. You only need to write that playbook once. Every time a new NTP key needs to be deployed, simply add the new key to the single copy of the NTP authentication keys, which is done on the control node, and Ansible will take care of the rest for you. What used to be a process that took more than an hour to complete can now be done in a few minutes. Since both NTP keys, configuration files, and the Ansible playbooks themselves are all regular text files, these can be managed in a revision control system, such as GitLab, for example. For the files that contain sensitive information, such as the NTP keys, Ansible provides support for encryption out of the box. After using Ansible for some time, we realized that there was a lot of copy pasting of long Ansible commands, so a simple menu-driven interface was created to simplify and streamline the whole process even further. Again, in the spirit of keeping things simple and using free and open source tools already available in most Linux distributions, the dialog tools were used to build a simple text-based menu system. Using text-based user interface has the advantage that it works remotely over SSH without the need of a graphical desktop environment. With this approach, users do not need to remember the command line syntax and can simply select the action they want to perform and are prompted for the authentication credentials and decryption passphrase. This not only reduces the chances of frustrating syntax errors at the command line, but also minimizes the amount of time required for training new staff. Since almost everything you can do at the command line when you manually set up and configure a server can be done using Ansible playbooks, then it is possible to fully script and automate the server setup from scratch. Once the system is provisioned with a partition scheme and a base OS, we can rely on Ansible to take care of the rest of the server setup and configuration. This approach forces the system administrator to describe each task required in the setup using a language that is human readable with no room for ambiguity or misinterpretation. It also ensures that this documentation is always kept up to date as the system configuration evolves over time. Since Ansible provides a level of abstraction on top of the system level commands, upgrading to a more recent OS or deploying a newer hardware usually can be achieved with minor changes to the existing Ansible playbooks. This also reduces the overall risk because if something goes wrong, it is easy to roll back to the previous state by rerunning the previous version of the playbook. This is where revision control of playbooks and configuration files really pays off. Now let's switch our focus to the monitoring aspect of our system. An important aspect of running an NTP service is to be able to monitor its performance and know when things go wrong. At NRC, we have leveraged free and open source software and frameworks to implement an NTP performance monitoring and notification system. The NTP monitoring system, shown in the box at the center of this diagram, is set up and configured as a Stratum 1 NTP server using UTC NRC 1PPS signal from the lab as reference. A backup process takes NTP performance measurements of monitored servers using the cronid command. For this, the regular NTP protocol is used, so no changes are required on the NTP servers being monitored by this system. The NTP performance data collected is sent to a locally running Zabbix server, which is a popular open source software for IT infrastructure monitoring. Zabbix stores the data in its own database, and provides a web interface for users to visualize the collected NTP performance data. The data is also saved in a PostgreSQL database, which is independent of Zabbix. This is to allow us to implement our own database table schema and not be constrained by the data structure imposed by the Zabbix system. Zabbix is also configured to send notifications when anomalies with the monitored NTP server's performance are detected. In addition to being used internally to monitor the NTP servers, this system is also offered as a service to external clients. This is part of NRC's TimeLink suite of products and services. Here we can see a screenshot of a page of the Zabbix web interface for a Stratum 2 NTP server, showing data for offset, round-trip delay, reach, and stratum level. Using this web interface makes it easy to visualize historical data and identify anomalies, not only in the NTP server performance, but also related to the network. We also configure the system to send us email notifications when specific conditions happen, such as stratum level changes, large offset, or missing data. On the right, we see how this can be configured via the Zabbix web interface. Here are a couple of examples of the type of useful information that NTP monitoring can provide. On the left, we see an anomaly that was observed on the performance of a Windows domain controller. This particular loss of synchronization took several hours to recover. On the right, we see how the same tool can give us information about the health of the network. In this particular case, regular spikes in FTP offset measurements correlate with large network round-trip delays, most probably caused by periodic network congestion in this particular case. As future improvement to the monitoring system, we plan to replace Zabbix with Grafana. Grafana is a very popular open source analytics and interactive visualization web application that supports connecting to many different data sources. Using Grafana will simplify the design, allow greater flexibility with the structure of the data, improves modularity, and also allows us to leverage the latest developments being done on Grafana by the open source community. Also, by running Grafana on a separate server, this will reduce the load on the NTP monitoring system and completely decouples the NTP measurement component from the visualization and alerting framework. Here we see an example of the Grafana dashboard that shows NTP measurement offset and round-trip delay. So the key takeaway of this presentation is that free and open source tools are available to automate NTP server administration and monitor its performance. And it does not have to be complicated nor expensive. We've seen how Ansible can provide the tools necessary for automation, along with revision control of the NTP configuration and Ansible playbooks. We've also looked at how an NTP monitoring and alerting system was implemented at NRC using available software such as Zabbix, PostgreSQL, and Grafana. As future work, we are working on upgrading the Stratum 1 servers with new hardware, including building new timecode generators to replace the aging Leech system drivers. We are also interested in exploring avenues for performance tuning of our Stratum 1 servers, including using hardware timestamping capabilities for the input 1 PPS signal. And we are also in the process of deploying a new time dissemination backup site in Western Canada. This setup will synchronize to UTC NRC using Common View time transfer, and will have a local cesium frequency standard for extended holdover capabilities. Once completed, it will provide NTP, web clock, and TimeLink services to the general public. Thank you for your attention, and we'll be happy to take questions.
Thank you very much, Andre. One question in the chat so far about whether you can share your presentation. And I believe that Patrizia will make all the presentations available on the BIPM website for registered attendees. So if there are other questions, I invite people to post them in the chat or raise your hands. Okay, I don't see any questions, so let's thank Andre for his presentation. And I would like to thank everyone who participated. It's a technical exchange. Thank you for volunteering. Thank you for preparing your presentations and sharing your best practices with the community. It's greatly appreciated. I've seen a lot of technical questions, so that some of your ideas that you presented will be picked up and implemented in many labs across the NMIs. This is the list of our presenters. Thank you all again. I'm looking for your active, for more contributors to participate in our future technical exchanges. And that brings me to my last slide. We have a discussion forum that I have been advertising throughout this meeting all around. There are some questions about the use of the forum that were addressed to me in the chat on whether people couldn't see the reply option. So I'm going to work with Patricia together so we can make sure that that the forum is accessible and useful to everyone. So please use it. Please post not just comments to this meeting, but in general, what topics you would like us to present at the future TAI meetings, technical exchange meetings. I think this is a good initiative, and a lot of people attend. I noticed the highest number of attendees was more than 150. So this is an excellent participation. Thank you. Suggest topics of interest to you, and then we'll send a call to volunteers to ask for volunteers to give presentations. Patricia, I see your hand is up.
Yes, and thank you, Marina, for the organization of this meeting. I see it is of great interest for all the laboratories, so it is a pleasure. And I also wanted to say, it seems that we just spoke in general of NTP today, but there are special issues like security or software for the monitoring and other activity that maybe would need some deep understanding and deep discussion. So if you are interested, please let us know. I think we can also invite maybe provider of equipment so they can explain what is available. So please let us know and we will be happy to organize a meeting like this one. And then let me tell you a word on the leap second. You know, it is one of my preferred topic in these years. Are you all aware that there is a possibility of a negative leap second? It is not sure, but the Earth is accelerating. So is your NTP service ready to deal with a possible negative leap second? The answer to the next time.
Always a relevant topic, the leap second. I see one hand up, Khalid. And the speaker heard. Patricia, are we going to take a screenshot of the attendees?
Yes, please, if you can switch on your camera, it will be, we will try. We are very many people, so let's see what we can do.
Please switch your cameras on if you can.
Please wait a moment. I see people smiling. Happy to see so many people and also smiling. So the picture is taken. Let's see how it will be. Thank you, Marina. Thank you to everyone.
Thank you, Patricia. Thank you, everyone. And let's continue the discussion online via emails, via forum, via future meetings. It was a pleasure to see you all, and have a good rest of your day or the night. Bye-bye.